Fun with derivatives.
All right. If you count counting and minor addition with my 4-year-old, then yes, I did, but otherwise no. Okay. Find the acceleration of the particle at t equals 2. Did you guys do a derivative of v? Yes. Okay, so really all you'd need to show on A is you'd write v prime of 2, and hopefully you used math 8 to arrive at that answer. Hopefully you were in radian mode when you did that. So v prime of 2 would equal A of 2, and what did you all get for that?
Negative 0.1329.
1329. You guys agree with that? Okay, cool. All right, so if you know what you're doing, A was probably over with pretty quick. Part B is the speed of the particle increasing or decreasing at t equals 2. Give a reason for your answer. If you think about it, didn't you sort of do a little bit of part B in part A? Because in part B, if you're going to decide about the speed increasing or decreasing, don't you need to know about acceleration at that time? What's the other piece of information that you need to know? Yeah, v of 2, yeah. So the only additional calculating you need to do is find v of 2, and v of 2 just essentially plug in, right? What's v of 2?
Negative 0.4363.
Negative 0.43, and you guys are doing 3 plus decimals and everything. You guys agree with that number? Okay, so then this is where we make our comparison. We would say this number is obviously negative, and from before we can say that A of 2 is also negative, because we did that in part A. And so since both of those numbers are negative, the speed is increasing. Yeah, so you'd say speed is increasing because V of 2 and A of 2 have the same sign. You could say are both negative. I like that better. Are both negative. Okay, so far so good, A and B?
So far so good.
Okay, part C. Find the time greater than or equal to 0 at which the particle reaches its highest point. Justify your answer. So you see those words, highest point. Do you guys think max when you see that? Highest point? You know, lowest point would be a min. Does that make sense, though? Like, even if you didn't see it right away, does that make sense? Highest, lowest?
Yes.
You're optimizing something, right? You're finding where it's highest, finding where it's lowest, furthest to the right, furthest to the left. Those are all optimization type words. So, if you were trying to optimize, it says highest point. When it says highest point, are we talking about like the highest acceleration, the highest velocity, or the highest position? Position is how I take that too, right? Point seems like a location, so we're going to be maximizing the position. So if you're trying to maximize position, you need to set position prime equal to 0/dne and see what happens with the sign change pattern with that. And so what is position prime?
Velocity.
V of t, velocity. So your first step, and this would be an important thing for you to write down, if you didn't write this down, you almost for sure would be missing out on some kind of a point or conceptual point on an AP test or one of my tests. So you want to set V of t equal to 0, and then please, for goodness sake, use the calculator to solve that equation, right? So you set V of t equal to 0. How many places did V of t equal 0? Was there just one? Okay. So when you solve that on your calculator, you got t is equal to what? 0.443. We all agree with that? Okay. So t equals 0.443. That's where V of t equals 0. So that is the only possible place where position is maximized. What kind of a sign change pattern did you see around that 0.443? A change from positive to negative. Okay, so there would be your justification. So you would say V of t change equals 0. I guess we already said that, so we don't need to say it again. Changes from positive to negative at t equals 0.443. Therefore, it reaches the particle, reaches the high point then. Notice it didn't give you like a closed interval. It did give you a closed interval on the left end with the 0. But you can notice, of course, that starting at 0 over to that 0.443, there's only positive motion. And then you only get that sign change from positive to negative just that one time. So I mean, your real only candidate is going to be that 0.443 number. Okay, still doing all right? Yes, remembering? Excellent. D. It just says find the time.
Yeah.
Yeah, you could find the max. You got yelled at? By Lenny? Oh boy. Let's start the year off right. No yelling. All right, so part D says find the position of the particle at time t equals 2. So to find the position of the particle at time t equals 2, you need to consider two things. You need to ask yourself, where did the particle start and how far did it move? Right? So where did the particle start?
-1.
Yeah, we can see that up there at the top. It says when t equals 0, the particle is at y equals -1. And so we're going to say that it started off at -1, and then we need to add to that the change in its position. So how do we find the net change in position when what we have is velocity?
Integral.
Integral, right? A definite integral from 0 to 2. Because 0 is our initial time, and 2 is the time that we're interested in. So be -1 plus the integral from 0 to 2. Should I put v of t right there, or should I put the v of t in absolute values? Should it be integral of v of t like I have up there, or should I slide those absolute values in there?
Keep it like that.
Keep as is?
Yeah.
What if I did put the absolute values in there? What might that do?
Total distance.
That's total distance traveled, and because we know this particle changed directions at 0.443, the total distance would be different from what that is, and that is displacement. So that would actually lead you to the wrong answer. If the particle never changed directions, then it wouldn't matter, would it? Unless it's moving left. So we don't want to mess with that unless it uses those keywords, total distance traveled. We want to leave the absolute values out of there. So use the Math 9 feature on the calculator. You add -1, hopefully fairly simple for you. What you get for an approximate position?
-1.3607.
3607, okay.
Oh, no, sorry. Sorry, it should be just negative point. No, you're right. Yeah.
Is that the right number?
That's right, yeah, it is.
Okay, you already added the -1 in there?
Yeah.
Okay, good deal. And so this is approximately equal to y of 2, the position at 2. And the final question then is the particle moving toward the origin or away from the origin at t equals 2? Justify your answer. And this depends on a couple of factors, right? Two things you got to consider here. So let me, okay, what do you guys think? Is it moving toward the origin or away from the origin?
Away.
Away, yes. So what would be, so let's put that in there. We'll say away from the origin. And what's the reasoning on that?
Signs.
Yeah, okay, some signs. Yes, I agree.
It's already to the left of the origin.
We're talking about vertical motion, though.
That's what to the bottom.
How do we know that we're below the origin?
We have a negative value. Negative value for position.
Yeah, so you could say y of 2 is negative, therefore the particle is below the x, or below the origin. The particle is below the origin. And what's the other thing? What do we have to compare that to?
Velocity.
Yeah, v of 2 is
Negative.
also negative. Therefore, let's say the particle is below the origin, and v of 2 is negative. I guess I could clean it up by just saying, therefore, moving away from the origin. You could draw a picture of it. If you drew a picture of it, you could say that when t equals 2, the position is down here somewhere. And since velocity is negative, it's moving down. So you really have to compare position with velocity there. Just because velocity is negative, I think the trap is for someone to say, hey, velocity is negative, therefore it must be moving towards the origin. Well, if position was positive, yes. But since position is negative and velocity is negative, it's moving away from the origin. Okay. How did that go? Remembering this well? I'm not surprised if you are, but it has been a few weeks, and even longer when you think about this particular set of topics. You guys have any questions before we move on to new stuff? Okay, good deal. Well, I do want to say this is a refresher for those that maybe had physics last year. This is kind of a primer for those that have never had physics. Maybe you've heard about vectors in the past. But we are used to doing these problems. I mean, you just proved that to yourself. You're used to doing these problems from the past. The truth is, what we just did is kind of a vector question. It's just that the left and right vector was 0 the whole time. It was just moving up and down. There was no left or right vector. Does that make sense? And so what we're going to be doing here is we're simply going to be allowing that other component of the vector to be something other than 0. Does that make sense? We kind of did an exercise with this when we introduced parametrics. Remember how we had the ball just going left and right? And we said, hey, what if we released the ball to move up and down too? And then you guys made the ball bouncing and it was moving left and right and up and down all at the same time. That's kind of what this is. And I think you'll find that if you are good at the parametric stuff, this will just flow right into that. And if you weren't good at the parametric stuff, this is a chance for you to kind of reinforce and relearn and get better at that, right? Because this is a lot of this is the same stuff. We'll just use some slightly different language. We'll use things like velocity, acceleration, and speed and position instead of just kind of the generic parametric stuff. Okay? Let's see here. Yeah, so as far as vectors go, a vector is something that has both quantity and direction, right? Magnitude and direction. And so you might see a vector represented with an arrow often. And a vector like that, we would say has components. So we would say that this vector is going up and right, if you will. And so there would be a rightward component, and we could call that Vx. There would be an upward component. We could call that Vy. Hopefully for obvious reasons with the x and the y, left and right, up and down. And so what we are going to be doing in this course is we're going to be really dealing with these components, right? We're going to do a little bit of the vector addition stuff, but it's not going to be the same as physics. It's going to be a little more formalized. But we'll basically be dealing with components. In your physics classes, when you guys did vectors and vector components, did you guys do I's and J's? Like bold I's and bold J's? This year you have, yeah. So in this class, we won't really do much with that. We'll use little bracket notation. I'll show you that in a second. Have you guys seen the bracket thing? I'll show you in a second. So anyways, the particle can move up and down, left and right, not just left and right or just up and down. It can do both, essentially. Okay. A few other vector basics here. Yeah, this is a good crossover right here. As far as developing these components go, this hopefully will go right along with what you've had in physics. If you have a velocity v and the direction is what we call some angle theta, then the x component is equal to v times cosine theta. The y component is v times sine theta. Physics people, does this go, like x goes with cosine, y goes with sine when you break down into components? That's all the same. That's nothing new. And then to calculus this a little bit, if you had velocity v, then the x position component would be the integral of that, right? It'd be v times t cosine of theta, and y would be vt sine theta. Don't worry about memorizing that. We'll actually go through some processes where we'll just kind of naturally go there. But I just want to point that out. And then one thing that's important for us in this class that you don't see in physics very much, in English units, feet per second, gravity is not negative 9.8. It's
27, 28,
10.
it's negative. Well, that's still kind of the metric thing. Oh my goodness. The guy not from the U.S.,
2.3.
the guy that's not from the U.S. knows it.
I got closest.
Negative 32, yes. And that's feet per second.
It's a little more than 2.
I like 9.8.
That's feet per second squared, by the way. I don't know why that's feet per second.
Secant?
Feet per secant squared? Man, I don't even know.
Like interface.
Feet per the derivative of tangent. This is getting really confusing. I'm getting confused, Darian. I'm just going to move on. Okay. So, how does this work? How does all this work with calculus? The good news is that you have done pretty much all this before. We're just going to be kind of putting things together in 2 dimensions instead of 1. So, when a particle is moving in 2 dimensions, all of a sudden the slope is not just 0, right? Because when it's just moving along the x-axis, the slope of the path is just 0, right? It's going left and right the whole time. Now, all of a sudden, it could be something other than 0. And so, hopefully, these 2 formulas expressing the derivative, or more specifically, the slope of the tangent line, or the second derivative, hopefully those 2 formulas look familiar. Do they look like those parametric formulas for the first derivative and the second derivative we looked at there? The exact same thing. So hopefully that's good news. You're not going to have to memorize any new formulas there. And so, yeah, when you're finding the slope of the tangent line, dy dx. And one reminder, I made a big point of this last semester. I'll say it again. No matter what you're talking about, if you're talking about x's, y's, and t's, later on if you're talking about r's, thetas, and t's, and other stuff, no matter what your variables are, the slope of the tangent line is always, 100% of the time, is always dy dx. The challenge is going to be, how do I relate the r's and the thetas, or the t's, or the whatevers, with the y and the x? That'll be the challenge. Slope of the tangent line is always, 100% of the time, always dy dx. So don't get confused into thinking that it's something else. Some other thoughts? Hopefully this all makes sense. X prime could also be written as dx dt. That's the rate of change of the x coordinate. Right? You could also think of it as the x coordinate of velocity, right? Or the x component of velocity. Y prime of t could also be written as dy dt. Of course, that's the rate of change of the y coordinate with respect to time. It's also the y component of velocity. Again, hopefully this goes with what you know from the past. Right? So we just did a bunch of this stuff. It was all in terms of y. We're going to have stuff with y's and x's and t's. Okay, and then as far as the notation goes, I asked you guys earlier if you had ever done stuff with like the bold I, bold J with vector notation. We will not be doing that. We'll be using these pointed parentheses, brackets, whatever you want to call them. Have you ever seen that notation? If you haven't, this is interchangeable with i's and j's. If you want to make the point that what you have is a vector, you don't do rounded parenthesis things. You do the pointed thing, pointed parentheses. That's the best way I can put it. Say again?
What does that mean?
That means that x of t, y of t is a vector.
Maybe like, what is a point in parentheses?
That's indicating that's indicating that what you have in there is a vector. Does that make sense? It's just it's a notational thing. So there very well might be. I've always just called them pointed parentheses. There could be a specific word for that.
Can you example of those?
Yeah, like what does it look like?
Which scientist came up with
there
it?
we go.
That would be position vector 2, 4. That'd be position vector 2, 4. This would be velocity vector negative 3, 7. So the way that you might be used to writing those would be this, 2 bold I plus 4 bold J. Same thing.
How do you know if it's position or velocity?
Well, you would have to be told that. You'd have to say, V of this, P of that, whatever. Yeah, so I use the brackets. I use the brackets because that's what the AP folks use. But the I and the J hat is perfectly acceptable. If you were kind of hooked on that from physics and you use that on the AP test or it's fine. No big deal. Okay.
So we can use the I hat and J hat on the
Yeah, so you want to be really careful with this. I don't know how picky they would get. If you're gonna use I's and J's, they have to be bold. Unless you use I hats and J hats, then they don't have to be bold. There's all sorts of rules about notation with vector stuff. Do you see what I like? Just did a double I, double J. Do you see how my I and J are a little more bold? I just made them fatter.
Pull out the Sharpie.
That's really all. Just get out the Sharpie and yeah. Then you're definitely making a point there. Yes, they're gonna know. Okay. So guys, the the point for all this is to just let you know that the pointed parentheses thing is a vector notation. Okay. Then, let me actually move this up a little bit. Some other things here. So I'd say these three things right here, these are three formulas you're going to want to have down for sure. Hopefully these will all make sense to you. Hopefully there's not, hopefully you'll be able to connect these with what you've done in the past. So, the speed of the particle is that expression right there. It's the square root of dx dt squared plus dy dt squared. What does that look like to you? It should look like something else. It is kind of a distance formula, Pythagorean theorem thing. Not quite. Not quite.
What's it called? Length of a curve.
Not quite.
Doesn't have an interval.
It doesn't have an integral.
It was where you add the things.
Right. Parametric.
That's what the last one is. You're missing the integral in the first one. Does this not look like, getting at physics people here, go ahead, Blake, say it.
Distance from the sun to the moon on the winter solstice.
Because you're using the distance formula.
That's right.
The Pythagorean theorem, okay. Physics people, do you guys know the word resultant? That's where you take the component and you find the hypotenuse, right? Doesn't this look like the hypotenuse? Pythagorean theorem. It is, aka the distance formula. Yeah, absolutely. So speed is essentially the x component of velocity squared plus the y component of velocity squared and the square root of that. This is also known as the magnitude of the velocity vector. Definitely a formula expression that you want to know. You want to know how to do this quickly and easily for speed.
You tell me it's not good.
Well, I don't know exactly what you're getting at there. I mean, I'm sure we could use that.
It was a blind guess.
I'm sure we could use that if we knew the appropriate distances and angles and everything. We could use that, yeah, we could. The angle of the object moving around at a particular point is going to be the inverse tangent of the slope. We'll look at this relationship quite a bit, especially when we get into polar as well. And then the final little formula here for you guys to know about is the distance traveled, and hopefully this looks extremely familiar, right? You guys are all kind of trying to point at that with the first one. But this right here, when you throw that integral from a to b on there, gives you the total distance traveled over that time interval from a to b. And this is the exact same formula as the one we learned for parametric arc length. Yeah, parametric arc length. And hopefully that makes sense that arc length would be the same thing as distance traveled. In this, we're just essentially calculating the length of the path that this particle traveled moving around. So in other words, if the particle started here and it went up and down and crossed over itself a bunch and ended up over there, we could find the length of that arc. Total distance traveled. Okay. These are some basics. We need to practice a little bit. We'll do one or two examples here, and then we'll be done. So let's check them out. I think. Yes, this is it. Okay. I really want to, I think for the most part, any concerns you might have, I think you're going to find are somewhat unwarranted if you're looking at this and you're thinking, oh my gosh, I've never had physics before, or it's been a long time, I feel really concerned about that. I think you're going to find that it's not too big of a deal. So hopefully number one here will help you see that. So it says no calculator allowed. A particle moves in the xy plane so that at any time t, the position of the particle is given by, and then you see you've got two components. You've got an x component for position and you've got a y component for position. And A says find the velocity vector when t equals 1. So you have a position and you're asked for a velocity, and so what's going to happen in there somewhere? Yep, you're going to have to differentiate. And here's how we do this. I'm going to say something along the lines of v of t equals x prime. Excuse me, that's not what I want to do. I just want to do this. You know what? Let's do this. I'll say, I wasn't going to do this, but let's do it like this. I'm going to say v of t equals vector bracket x prime of t, comma, y prime of t. To do this, you essentially just differentiate the x component and you differentiate the y component. So for this particular example, x prime, that's going to be super easy for you guys to find, right? X prime would be 3t squared plus 8t. What's y prime? Hello? What's y prime?
14 cubed.
All right. Okay, so that is your velocity vector at any time t. We want to know the velocity vector when t equals 1. So you'd say v of 1 equals, and then to get your final answer, you'd plug in a 1 for all the t's that you see. So at 11, comma 1. That means when v equals 1, the velocity vector is 11, 1. So that means the x component is 11 and the y component is 1. So is this particle, when t equals 1, is it headed up and left, down and right, up and right, left and down? Which way is it headed? Up and right, right? Because both components are positive. It's going up and right. Is it going more up or is it going more right? More right, right? More right, because the x component is a whole lot bigger than the y component, at least at this particular point in time. Question, McKenna?
Does it matter if you do like that formatting or the one where it's like dy dx, like that?
So be careful with that. So when you find dy dx, you are finding the slope of the tangent line to the path of this particle moving around. That's not what it's asking for.
Okay.
Be really careful with that. So later on, you're going to see questions where you'll get some, question stem like this, and it's going to ask you like a series of questions. It's going to say, what is the velocity vector? What is the slope of the tangent line at that point? And all these things are related, but they're not all the exact same. So I would separate them out. I would write this in vector form, not as a slope of a tangent line. Clearly related, but not the same. Okay. Anybody else? Okay. And then B, find the acceleration vector for when t equals 2. Isn't this just another level of a derivative? This is all stuff you've done in the past. We're just doing it in 2 dimensions instead of 1 dimension. So we would say a of t is equal to 6t plus 8, comma, 12t squared minus 6t. And of course, we are interested not just in a of t, but in a of 1. So a of 1 would be the plugging in of 1. So I'm getting 14, comma 6.
It says that t equals 2.
Oh, t equals 2? Who switched that? That's a bad question. I don't like that. T equals 2, okay. So t equals 2 would be what, 20?
4 times 12.
Comma, 48 minus 12, 36. 20, comma 36. Okay. Let's do one more. This will give us plenty of room on Monday. So number 2 says a particle moves in the xy plane. So for any non-negative time, the position vector is given by those 2 components. Find the magnitude of the velocity vector when t equals 1. So here's where that formula would come into play. You would say, you look at these keywords, magnitude of the velocity vector. That's also known as, that's another term for which other word? Speed specifically, right? The resultant without the direction. Yeah, speed. So you'd say, hopefully the formula is square root of dx dt squared plus dy dt squared. So of course, in order to do this, we need to know what dx dt is and what dy dt is, but thankfully these are pretty easy to calculate. So let's see here. dx dt would just be 2t plus 3. And then don't forget squared. Plus 3t squared minus 6t squared. So this would be a formula for the speed at any time. Of course, we want to know the speed at 1. So at t equals 1. Let's see here. 2 plus 3 is 5. I know. Squared is 25. 3 minus 6. Negative 3 squared is 9. Did you guys come up with the square root of 34? Okay, so that would be the magnitude of the velocity vector, aka the speed of this particular particle when t equals 1. All right, this is a good start. We'll do another kind of warm-up practicing thing on Monday because I know you're not all the way back yet totally. And we'll push to try to finish most of this by the end of Monday. Hope you guys enjoy your weekend. See you Monday. Glad you're back.